Welcome to Chapter 7 of Surviving Statistics. In this chapter, we're going to continue on our discussion of probability distributions. This time, we're going to cover uniform probability distributions and the normal probability distribution, which we'll be working quite a bit more with as the chapters continue. Well, hopefully you recall from the previous chapter that a probability distribution lists all possible outcomes from an experiment. It also lists the probability for each possible outcome. Well, we also talked about two different kinds of variables that can result from measurements. We talked about discrete, which typically are going to be counted, and then we talked about continuous variables that can assume any value within the range. So for example, we talked about the weight of a 2-year-old child selected at random. That's a continuous variable. They could weigh 20 pounds, 23 pounds, 22.9 pounds. So the two types of distributions we're going to cover in continuous probability distributions are uniform and the normal distribution, which uses the normal curve that, like I mentioned in the last slide, we'll be using quite a bit. All right, we're going to begin by talking about uniform probability distributions. In a uniform probability distribution, the probability of any one particular outcome is exactly the same, equal to any other. So let's use as an example, you're at a bus stop, you're waiting for a bus. There's no bus there, and so now you have to wait for the next bus. There's no schedule of arrival times, but you just happen to know that a new bus arrives every 60 minutes. So since you don't know when the last bus was here, your waiting time could be anywhere from 0 to 60 minutes. And the probability of you waiting 50 minutes or 0 minutes or 1 minute is uniform. They all have the same probability. We represent uniform probability distributions with a rectangle, beginning with the minimum value and the maximum value. And so this rectangle that you're looking at here has a minimum waiting time of 0. The bus might just arrive just as you got there, or the maximum of 60 minutes because a new bus arrives every 60 minutes. And the probability is equal. The probability of you waiting 10 minutes is equal to the probability of you waiting 50 minutes or even 60 minutes. So if you're sitting at this bus stop and there's no bus, invariably you're going to want to know a few things. You're going to want to know perhaps what is the expected wait time, or in other words, what is the mean? What is the probability you're going to have to wait 5 minutes or less? What's the probability that you're going to have to wait 45 minutes or longer? And if that's the case, you probably want to call an Uber. So the first question we want to answer is, how long do I expect to wait here? In other words, what is the average or the mean wait time? Well, we compute the mean very simply. We simply add the minimum plus the maximum. In this case, 0 is the minimum and 60 is the maximum, and we divide that by 2. So 60 divided by 2 is 30. The expected wait time is 30 minutes. So the next question we're going to answer is, what is the probability that we're going to have to wait 5 minutes or less? So if you look at the rectangle on the screen here, you can see that we're only considering the probability of just a certain portion between 0 minutes and 5 minutes. So the first thing we have to do, number one, is define the probability of any one point. And the probability of any one point is going to be 1 divided by b minus a. Well, again, b was 60 and a is 0. So the probability of any one point on there is 1/60th. So the next step is to determine the number of units that we're working with. Well, we're working with 5 minutes or less, and so that ranges from 0 to 5. So we have 5 units. Then we're going to multiply the number of units by the probability of each unit. So we had 5 times 1/60th, or 5 divided by 60, we end up then with 0.0833. And so we have about an 8% probability of waiting 5 minutes or less for the next bus. We saw that we didn't have a very large probability of waiting 5 minutes or less, so what if we have to wait more than 45 minutes? And we want to call that Uber or Lyft or somebody to give us a ride here. So in this case, we figured out the same way. We're working with 15 units between 45 and 60. We know the probability of any one unit is 1/60th. So in this case, we have 15 divided by 60, and we then come up with a 25% of waiting more than 45 minutes. That's a long wait. We've already introduced you in previous chapters to the normal probability distribution, but the normal probability distribution is represented by the bell-shaped curve. And in a perfectly normal distribution with no skewness, the mean, the mode, and the median are all the same. And the mean, the mode, and the median are all represented by the top of the curve. The standard deviation is also an important value. We talked about that already a little bit when we introduced you to the concept of the empirical rule. Remember, the empirical rule told us how much of the curve lied within plus or minus 1, plus or minus 2, or plus or minus 3 standard deviations of the mean. Well, now we're going to go ahead and use that empirical rule, and we're going to build on that a little bit to actually come up with probabilities under the curve. Let's just run through those numbers real quickly with the empirical rule. That approximately 68% plus or minus 1 standard deviation, 95% plus or minus 2, and practically all, or 99.7, plus or minus 3 standard deviations of the mean. We need to talk about working with z-scores. And at first glance, it seems like z-scores are an extra step, but trust me, they're going to make your life a whole lot simpler in the long run. So when we talked about the empirical rule in this chapter and in other chapters, we had a very simple example with the example that you see on screen here with a normal curve. The mean is 100, the standard deviation is 10. And so that we can see that the range between the value of 90 and 110 actually is plus or minus 1 standard deviation. But when we're dealing with means of maybe 1022.83 and standard deviations of 63.9, this becomes very, very complex to work with. And so a z-score allows us to compute how many standard deviations a value deviates from the mean. And it's a standard value that we're going to work with. And the way we compute a z-score is we simply take the value that we're working with, 110 in this case, or 120, we're going to subtract that from the mu, from the average, and we're going to divide that by the standard deviation, which gives us a z-score. Now we'll go ahead and see how that works in the next slide here. Well, let's start with a very simple example of how to compute a z-score. So in the illustration that we're working with here, we have the mean of 100 and a standard deviation of 10. And so using this formula, let's assume that we want to know what the z-score for 110 is. In other words, what's the probability of choosing a data point 110 or higher? And so we're looking for the area of the curve that is at 110 and higher, which would be to the right. So with this illustration, it's easy to use these numbers to determine what the z-score is. 110 minus 100 divided by 10 equals 1. We end up with a z-score of 1, which is how many standard deviations that deviates from the mean. All right, to remind you, the question that we're trying to answer here is what is the probability of finding a score at random that is 110 or greater? Now we've computed a z-score of 1. And so now with the normal distribution table that you see on the screen here, we can see that we're looking at the area that is 1 standard deviation greater than the mean, and that also includes all the other area to the right of it. So now what we're trying to figure out is how much of the area of the curve is within that area. So in other words, if I had a score of 119, that would also fit the area that I'm looking for. I'm looking for a value of 110 or greater selected at random. All right, we've computed a z-score of 1. And so remember, we're trying to answer the question, what is the probability, the likelihood of finding a value 110 or greater by surveying an individual at random? So in order to do that, we have to remind ourselves that the normal curve is separated in half. Half of the values are less than the mean, half of the values are greater than the mean. Once we remember that, we're looking for the area under the curve that is more than 1 standard deviation away. Now, we can use software programs like Excel, or we can use predefined tables to actually figure out what that value is, and we'll go ahead and show you a table on the next slide to make this very easy. Remember, what we're trying to figure out here is the area under the curve from 110 or above. We computed a z-score of 1, and now we're looking at a table, a standard normal distribution table or z-score table, that helps us locate a particular value or an area associated with a z-score of 1. Now you'll notice that on the far left column it says z0, z equals 0.1, and so we scroll down until we find the 1. But notice also we have additional columns. So if we had, for instance, a z-score of 1.01, we would move into the second column and find a different z-score, or 1.03, 04, or 5. In this case, though, we're looking at 1.00, and so the area, or the z-score value that we're looking for, is 3413. Now, it's not quite that simple. That really hasn't solved our problem in this case, but it gives us a good start, and we'll figure out how to solve it in the next slide. So when you look up a z-score on the table, what you're finding is the area under the curve related to that particular z-score. Now, with a z-score of 1, the table gave us a value of an area under the curve of 0.3413. Now, really that isn't our answer, because we're concerned about the area of the curve to the right of a z-score of 1. As you see on the screen here, we're concerned about the shaded area. Now, of course, I already have the numbers here, but let's show you how we came up with those numbers. Remember that we divide our bell-shaped curve into two halves. 50% of the values lower than, 50% of the values higher than. We're looking for values that are higher than the mean with 110 or above. So the area under the curve related to our z-score of 1 is 0.3413. But that value, the 0.3413, is the area of the curve represented by the mean to the standard deviation resulting from the z-score. In other words, from the mean to one standard deviation away is 0.3413. We're concerned about the area to the right of that. And so we know that the whole half, of course, is 50%. So we have to subtract the area from the mean to the standard deviation referenced by the z-score. We subtract that area from 0.5. So 0.5 minus 0.3413 equates to an area under the curve of 0.1587. So the answer to our question then becomes the probability of finding any one data point at random with a value higher than or equal to 110 is 15.87%. So remember, the area that you're finding when you look up a z-score is the area from the mean to the standard deviation represented by that z-score. You can also skip using the table and use Excel if that's a tool that you like to use to compute areas under the curve. However, it's a little different value than you'll see in the table, so I do want to talk about how it's a little bit different. The first thing is you do not have to actually compute a z-score. Using Excel's normal.dist function, you can simply pop in the values. And so in this case, the example that we were using was x being 110 or greater, the mean of 100, the standard deviation of 10. We put in the cumulative of true, and that's just a value that we have to pop in there, but when we do that, we end up with an area under the curve of 0.8413, which is significantly higher than what we saw in the table of 0.34134. And the reason for that is it includes both sides of the curve. It includes the side lower than the mean and also the side greater than the mean. We are really only concerned about the values that are higher than the mean. And so we're going to subtract 0.5 from the 8413 that Excel computed for us. And then once again, we see the 0.34134 that we found in the table. But remember, because we're looking for 110 or greater, we're looking for that tail to the right of one standard deviation, or a z-score of 1. And so we'll have to subtract 0.3414 from 0.5 to end up with the area under the curve that would represent 110 or greater. Well, that's really it for Chapter 7. Let's go ahead and review what we talked about. We talked about a uniform distribution, and that's when the probability of any one outcome is equal to that of any other. We compute the mean of a uniform probability distribution with a plus b divided by 2. Remember, the a is being the minimum value and b being the maximum value. We divide that by 2. We get the probability of any one value in that uniform distribution. In this chapter, we also talked about normal probability distributions. Remember, a normal distribution is represented by a bell-shaped curve, and when it's perfectly aligned, the mean and the median and the mode are all the same value, and they represent the highest point in the curve. To compute areas under the curve, we used z-scores. The formula for computing a z-score is simply the value that you're looking for minus the mu divided by the standard deviation. And to find the area under the curve or the probability associated with the z-score, you can use the standard normal distribution table, or you can also use Excel. And remember, all of these lessons are based on my textbook, Surviving Statistics, which is available on Amazon. And do remember to check out my website for downloadable files, calculators, and other resources.